Hello, welcome to our first video. Hopefully this works alright. Please be patient with me. Okay, so Surds, this is our topic, and today we're looking at part 1, which is the real number system. So that's our heading for today, the real number system. Now the real number system can be broken up into two parts. There is the rational numbers and the irrational numbers. Okay, so we'll break our page up into two parts. Let's start with the rational numbers. Rational numbers are what we're more familiar with. Rational numbers really are any number that can be written as a fraction. So let's write that definition out, but we'll just write it a bit more exact. So any number that can be written as a fraction in the form P on Q. In the form P on Q. Because that's, we see fractions something on something else, where P and Q are integers. Right? So, 1, 2, 3, 4, etc., or -1, -2, etc. Okay, integers. However, there is one integer that Q cannot be, right? Because Q is on the bottom of our fraction. What can we not have on the bottom? 0. So Q can't be 0, but otherwise, any number that can be written in the form P on Q, where P and Q are integers, well, that number is rational. So let's think we've got just integers. Remember, any integer can be put over 1, and so it can be in a fraction form. And we've got fractions themselves. We've got mixed numbers. A mixed number, if we want, we could just put into an improper fraction. Okay, so that would be in the form P on Q. So mixed numbers are good, they're rational. And then when we look at decimals, if you've got a decimal that stops, so it terminates at some point, well, that can be written as a fraction. And then if you've also got a decimal that goes forever, but it has a pattern, so a recurring decimal, that is also a rational number. It can be written as a fraction. So think of, let's say, 0.66666 repeater forever. That's just 2/3, right? So that's rational. All right. So we've had a little look at rational numbers. So everything that's left must be irrational. Okay? Everything that's left must be irrational. So let's define that. These are numbers that cannot be written in the form P on Q. Okay, and also when we look at them as decimals, they go on forever, but there's no recurring, there's no pattern. Okay, so the decimals go on forever with no pattern. Now you guys know some irrational numbers already. Have a think before I say any. What are some irrational numbers that you know? Pi, that's a common one. That's irrational. Square root of 2, that's irrational. Here's some other ones. The cubed root of 4, or the square root of 3, Or even if we take the square root of 3, which is irrational, and add 2, it's still irrational. The decimals go on forever. So there's some examples. Alright, so now what we're going to have a look at is, can we plot irrational numbers on the number line? Irrational numbers on the number line. And the answer, in short, is yes. Just because we can't get an exact decimal doesn't mean we can't put them on the number line. So let's write that down. Although we cannot get an exact value, an exact decimal value, sorry. Let me get rid of. Alright, so although we cannot get an exact decimal value, because we can actually get an exact value, like pi is an exact value, but we can't get an exact decimal value. But yeah, so although we can't get this exact decimal value, their position can still be plotted. Okay, so let's draw a number line now. I'll try and insert one. Oh, yeah, there it is. Let's bring that down. Okay. So we'll stretch our number line out. We'll just go, we'll say start at 0 on the left. Here's 0, 1, 2, 3, 4. Alright, now before we get into even plotting, let's think about a right-angled triangle. Okay. It's got base length 1 and height of 1. Okay, so base length of 1, height of 1. It's a right angle, and so the hypotenuse is joined up there. Okay, now obviously the hypotenuse of that triangle is an actual length, right? We can see it right there. But what is the length of that hypotenuse? Okay, remember we can use Pythagoras' theorem. The length of the hypotenuse will be the square root of the two shorter sides squared and added together. So square root of 1 squared plus 1 squared. Now 1 squared is just 1, 1 plus 1 is 2. So in this triangle, the hypotenuse has length square root of 2. Okay, so let's put that on. Oh, sorry. Let's put that on here. We'll label that square root of 2. Okay, so the square root of 2, we've already talked about how that's in the irrational number though. But we can see it's got a length here, and if we took that hypotenuse and just laid it down flat on our number line, it would sort of end up around here somewhere. Out there. Okay, so we've just shown that right there we can plot the square root of 2. What's another one? I mean, pi, we talked about how pi is one that we already know. If we put that into our decimal, we'd get approximately 3.14. Okay, so that means pi can be plotted about there on our number line. So we can plot our irrational numbers. That's the moral of the story. Alright, let's have a look at some examples to finish off our first digital lesson. In these examples, we're just going to ask ourselves, is each of the numbers that we're looking at, are they rational or irrational? Okay, that's the question for these 4 examples that we're going to do. Alright, number 1. Negative 39 on 17. Is that rational or irrational? Now if we go back to our notes, okay, we can see that fractions are in the rational number system. So this must be rational. Alright, example 2. 0.3 with a little dot above it. And what does that little dot mean? It means the 3 keeps repeating forever and ever and ever and ever. So this goes forever. Does that mean it's irrational? Well, going back to our notes, let's have a look up here. Recurring decimals. They're in the rational numbers as well. So, oh man, sorry. How good is Control Z? Alright, going back to number 2, this is a recurring decimal, so this is also rational. Alright, example 3. The square root of 49. Now the square root of 49 is just 7, right? And 7 is an integer. 7 is an integer. So that's also rational. Let's see if I can get back down the page. Oh man. Okay, so rational. Now that might seem like a bit of an obvious one, but as you can see there's a lot of surds that have square roots, like the square root of 2. And so people can start to think whenever they see a square root sign that it must be an irrational number. But just think about it for a little bit. If it's the square root of a square number, well obviously, okay, it's not irrational. It has to be rational. And even if you can take the square root of something and get a fraction, well then that's also rational, not irrational. Okay, so just something to be careful of. Alright, last example. Since we're talking about 7, what about the square root of 7? Okay, now we know 7 is not a square number, and if we put the square root of 7 into our calculator, we get 2.64575 and so on. Okay, seems like it's not going to stop anytime soon, and there's no pattern that we can see. And this is in fact an irrational number. Alrighty, well, that brings us to the end of our first lesson. We've had a little look at the real number system as being broken up into rational numbers and irrational numbers. If we can write something as a fraction, it's rational, and if not, it has to be irrational. Irrational numbers can be plotted on the number line, like we showed with square root of 2 and pi. And then we had a look at a couple of examples deciding on if something is rational or irrational. So have a go at the exercises now. Good luck, and I'll see you in class.